Hello children, today we will study Unit 9 of Chemistry, that is coordination compounds. Now if you see carefully in this slide, two molecules are shown to you and both these molecules are very important from biological point of view. The first compound is or pigment is hemoglobin. So this is red pigment found in blood and is responsible for giving red color to the blood as well as helps in carrying oxygen. Similarly, the second compound is chlorophyll, which is green pigment found in green plants and is responsible for photosynthesis. Now, if you see these two compounds, then these two compounds have quite a complex structure. In this particular compound, both have few things in common. The first thing is both have metal atom centrally placed. In hemoglobin, iron is the centrally placed metal atom and in chlorophyll, magnesium is there. Now, if you see carefully, this iron atom gets bonded to nitrogen with the help of coordinate bond. Nitrogen will have lone pair over it and that lone pair is shared as well as donated with iron. So, coordinate bond will be there. Similarly, coordinate bond will be found between magnesium and the surrounding molecules. So such type of compounds which have coordinate covalent bond between metal atom and the surrounding molecules are said to be coordination compounds. We will study about coordination compounds, their naming, their importance, their classification, and many more properties. So first of all, coordination compounds. So first thing about coordination compounds is they are complex compounds. These have complex structure. So that's why they are also called as complexes. Second important thing about these complex compounds is these have coordinate covalent bond in them. Coordinate covalent bond in them. Now this coordinate covalent bond will be present between metal atom or ion and anions or neutral molecules. So coordination compounds are complex compounds. They have coordinate covalent bond in them and that coordinate covalent bond will be present between metal atom or ion and surrounding anions or neutral molecules. Now, these complex compounds are mainly formed by transition metals. So, transition metals will make these compounds. In previous chapter, we have already studied why transition metals only form complexes. First important property which is present in transition metal, it is small in size. And because of small size, it has high effective nuclear charge. Effective nuclear charge. Due to high effective nuclear charge, it can accept the anions or neutral molecules towards it. Since in these compounds coordinate bond is formed and coordinate bond formation involves sharing of electron pair given by single donor atom, given by one atom you can say. In normal covalent bond, if single covalent bond is there, then the shared pair of electron will be contributed by both the atoms. But in coordinate bond, one of the atom will donate and share its electron pair to make covalent bond. For example, ammonium ion. In ammonium ion, both type of bonds are there. That's why I have taken this example of ammonium ion. In ammonium ion, nitrogen has one lone pair, and like this, nitrogen has 5 valence electron, 1, 2, 3, 4, 5. Now, 4 hydrogen atoms are there. So first, hydrogen has 1 electron. So this yellow electron belongs to hydrogen like this. So this bond is normal covalent bond. Why this is normal? Because the shared pair of electron is contributed by both nitrogen as well as by hydrogen. But next bond is formed between proton. Proton means H plus, and H plus means it has 1 electron and that also being lost by it. So proton has no electron available for bond formation. Now what will happen? This electron pair of nitrogen will be shared as well as donated with this proton, and in this way this bond is coordinate covalent bond. So coordinate covalent bond involves sharing of electron, but shared pair of electron will be contributed by single atom. It is shown with arrowhead, so you can show it like this. This is normal covalent bond between 3 hydrogen atoms, and this is the coordinate covalent bond. So in this way, ammonium ion can be shown. So similar type of bond should also be present in coordination complexes, and this coordinate bond should be present between metal atom and anions or neutral molecules. Now, since only one atom is contributing the lone pair in order to make bond with the central atom, therefore the central atom must have vacant orbitals to accommodate lone pairs given by surrounding molecules or anions. This is the most important point which is present in transition metals, and therefore these make complexes in large number. Although chlorophyll has magnesium in it, so there are other metals also which can make complexes, but most of the time complex compounds are made by transition metals, that is d block elements which have vacant d orbital available to them. Now, in order to understand the complex compound, we will take one example. This is the example. Cobalt, 6 ammonia molecules are there, and Cl3. This is the compound. Now, in this particular compound, this cobalt is the central atom. Central atom means all the ammonia molecules will be surrounding it. And cobalt is metal which belong to transition series. So central metal atom is cobalt. Now since it is central atom, and in this case it is having +3 charge, that I will tell you later on how it is in +3 state. So this has +3 charge, it means it is electron deficient. Since it is electron deficient, therefore it it will behave as Lewis acid. So always keep this in mind that the central atom behaves as Lewis acid. One more property because of which it acts as Lewis acid is it has vacant d orbital. And it is this vacant d orbital which accommodate the lone pair given by the ligands, either in atomic state or in hybrid form, mostly in hybrid form. Now the second is ligand, or these, in this case, this ammonia molecule. This ammonia molecule is the molecule which is surrounding the cobalt atom. So this should be neutral molecule, or you can say in most of the time it can be neutral molecule, or it can be anion. Neutral molecules or anions. But the neutral molecule must have lone pair on it. So they are basically electron rich species. And since they are electron rich species, they have lone pair. So they are electron pair donor. And you all know electron pair donor are said to be Lewis base. So these are Lewis base. So what will happen? This ammonia molecule will donate and share its electron pair because it has one lone pair of electron over it, because it is very good Lewis base. And cobalt being electron deficient, or Lewis acid, as it has vacant d orbitals, so it will accommodate the lone pair given by it. So in this way, coordinate covalent bond will be formed between the ammonia molecule and the cobalt atom. And if such type of bond is present in any compound, then that will be called as coordination compound. Again, we will take the same example. CO, NH3, whole 6, 3 plus, Cl3. Now in this case, you already know this cobalt is central atom, central metal atom or ion. This ammonia is ligand or neutral molecules. The other name is called as, or given to it is, ligand. That I will tell you later on. So these neutral molecules which surround this cobalt, these two together will be called as coordination entity. Coordination entity. And always remember, this coordination entity will always be written in square brackets. Second, outside this square bracket, these 3 chloride ions are there. These ions are called as counter ions. Counter ions. These counter ions simply balance the charge present on complex part. So they simply balance the charge present on complex part. For example, in this case, if 3 chloride ions are there, we know chlorine, since has 7 electrons in their valence shell, so it needs one more electron, so it has -1 charge. So 3 chlorines are there, so it means it has 3 minus. So if 3 minus charge is present on 3 chloride ions, it means this complex part will be cation and it will have 3 plus charge over it. In this way, whole of this compound will become neutral. So coordination entity you can define as it consists of central atom, central metal atom, bonded to neutral molecules or ions. It consists of central metal atom, here uh, central metal atom, bonded to neutral ions or molecules, right? It means you can say central metal atom plus neutral molecules. Or anions. They together will make the coordination entity, and it will always be written in square brackets. Whatever outside it, that will be counter ion. Now, counter ion can also be cation. For example, if I write K4, K4 FeCN whole 6. Now, in this particular case, one potassium ion has +1 charge, 4 potassium ions are there, so 4 plus, and this complex part, coordination entity part, has -2 charge over it, right? This is coordination entity, so it has -2 charge over it. In this case, this counter ion, potassium ion is cation. So counter ion can be an ion, they can be cation. Similarly, the coordination entity part can also have positive charge or negative charge. If the complex part has positive charge over it, this coordination entity part has positive charge over it, then such type of complexes will be called as cationic complexes. So what are cationic complexes? Cationic complexes are those in which the coordination entity or the complex part, that is the part which consists of central metal atom and ion and ligand or neutral molecules, that part which is written in square bracket, that is cation. Similarly, in this case, the coordination entity part is negatively charged. So such type of complexes will be called as anionic complexes. So on the basis of charge, two types of complexes are there. Now next important term is ligand, or you can call it ligand. Ligand usually written like L minus, because I've told you ligand should always be electron rich. It should be electron rich. So in most of the cases, either they are neutral molecules having at least one lone pair. They should have at least one lone pair. Or they can be neutral molecules. They can be anions. That is negatively charged. Negatively charged, say Cl minus, OH minus. So all the negatively charged ions, as they have negative charge, means they are electron rich. So they can also make coordinate bond by donating as well as sharing its electron with electron deficient central atom, and thus they make coordinate bond with them. So Third point is ligand should, in most of the cases, behaves as Lewis space. Very rare positive ligands can also be there, but they are very rare. So in most of the cases, it is considered that ligand either should be electron rich or neutral molecule with at least one lone pair of electron with them. Now these ligands are classified into various categories. So first, types of ligands on the basis of charge. On the basis of charge. So broadly, three types of ligands are there. One is positive ligands. Second is negative ligands. And third is neutral ligands. Now, since ligand has to make coordinate bond with electron deficient central atom, so in most of the cases, the ligands will be either negative or neutral. As the name suggests, negative ligands are those which have negative charge. So all the negatively charged ions, they will be regarded as negative ligand. Like this. All those species which have negative charge on them, they all will be regarded as negative ligand. And many more are there. Chloride ion, hydroxide, sulfate ion, oxalate ion. This is oxalate ion, formed by oxalic acid by removal of 2H ion, cyanide ion, etc. So all negatively charged ions. Neutral molecules which can behave as ligand, they should have at least one lone pair of electron on them. So ammonia is a very good ligand. Then water is also very good ligand because it has lone pair of electron on oxygen atom. Similarly, En or ethane 1,2-diamine, ethane 1,2-diamine. Triphenylphosphine, triphenylphosphine, phenyl group, phosphine. This is also negative ligand. Then carbon monoxide, this is also negative. Sorry, triphenylphosphine, carbon monoxide, they all are neutral ligands. They have no charge on them, but all have at least one atom having lone pair. That's why you can call them neutral ligand. So these two are the only type of ligands which will be found mostly. Positive ligands are found very rarely. So nitrosonium ion, NO+, this is an example of positive ligand. Similarly, N2H4 plus, N2H5, sorry, N2H5 plus, just wait, N2H5 plus. But these ligands are very rare, because it is very difficult. When positive ligands are there, it means they are electron deficient, and if they are electron deficient, then it is very difficult to make coordinate bond with the metal atom. So these are very rare ligands. So mostly negative and neutral ligands are there. Second type of class on the basis of denticity. Types of ligands on the basis of denticity. Just wait. Yes, on the basis of denticity. Now this is the new term for you, denticity. Now what is the meaning of this word denticity? In order to understand this, Again, we will take one example. Say we have the same example, CO, NH3, whole 6, Cl3. Now in this particular complex, the complex part or coordination entity consists of cobalt and ammonia. Now, cobalt atom is surrounded by 6 ammonia molecules. If you see the structure of ammonia, then it is having one lone pair of electron over it like this. So this lone pair of electron will be donated as well as shared with this cobalt atom. So coordinate covalent bond is formed. One coordinate covalent bond is formed by ammonia molecule. Since this ammonia molecule has only one donor atom, right? Ammonia has only one donor atom, that is nitrogen, and only one is involved in bonding, so its denticity will be 1. Similarly, if we take an example of CN, cyanide. Now in CN, 2 donor atoms are there. One donor atom will be carbon and another donor atom will be nitrogen. So in cyanide, 2 donor atoms are there, but at a time, only one is involved. At a time, only one is involved. So although 2 ligating sites are there, but at a time, since one is involved, so it means its denticity will also be 1. Now by these two examples, it is very much clear that denticity is basically the number of donor atoms available on any ligand for bond formation simultaneously, right? So number of donor atoms available to a ligand simultaneously, or you can say at a time, for bond formation, for coordinate bond formation. Whenever I say bond, it means I am talking about coordinate bond only, because coordination compounds have only coordinate bond in them. So number of donor atoms available to ligand simultaneously, or you can say at a time, for coordinate bond formation. That is called as denticity. Now one more example we will see, ethane 1,2-diamine. Now in ethane 1,2-diamine, ethane, so 2 carbon atoms will be there. Diamine means 2 amino groups will be there, NH2 and NH2. Now one lone pair of electron is present on this nitrogen, and one electron pair will also be present on this nitrogen. Now if this is the central atom, Mn plus, now what will happen? Both of these will donate as well as share their electron. So this is also making one bond and this is also making one bond. So both are making bond at a time. So it means its denticity will be 2. Denticity will be 2. I hope the concept is clear to you. So on the basis of denticity, you can categorize the ligand following categories. The first one is monodentate. Second one is didentate or bidentate. You can also call it didentate. And third one is polydentate. Now if the denticity is 1, denticity is 1. If denticity is 2, if In this case, denticity is more than 2. Then you call it polydentate. Now, denticity 1 means only one donor atom is there and only single donor atom at a time is involved in bond formation. So Cl minus, NH3, Cn, all these are monodentate ligands. Water is also monodentate ligand because it also has only one donor atom available to it, that is oxygen, and at a time only one bond is formed by oxygen atom. Now didentate, I have shown you the example of En, that is ethane 1,2-diamine, 1,2-diamine. Then another example we will discuss, the abbreviation is OX, and OX means oxalate ion. All of you know very well, oxalate ion is formed by oxalic acid, and oxalic acid is COOH and COOH. Now, when this hydrogen is removed from it, like this, then due to the removal of hydrogen ion, it will acquire -1 charge over it, like this. Now, if this is the central atom, say Mn plus ion charge, now what will happen? This electron pair which is present on this oxygen, that will be involved in bonding, and similarly this will also be involved in bonding. So single oxalate ion has two donor atoms and both are involved in bonding at a time. So denticity will be 2. Similarly, the best example of hexadentate ligand is EDTA ion. So EDTA ion is the best example of polydentate ligand. Now in this case, the full form of EDTA is ethylene diamine tetraacetate ion. Diamine tetraacetate ion. Now it is very simple to draw the structure of this ion. Now ethylene means 2 carbon atoms are there, like this. Amino means 2 amine groups are there, like this. The structure of ethylene diamine, which we have made earlier also. So this is ethylene diamine, but ethylene diamine tetraacetate ion. Tetra means you have to accommodate 4 acetate ion. Acetic acid is CH3 COOH. It will lose 1 electron and gets converted into acetate ion. So CH3COO is acetate ion. Now you have to accommodate 4 acetate ion. Since 4 acetate ions are there, so 2 bonds will be formed like this. But in doing so, these hydrogen must be removed. So these 2 hydrogens will be removed in order to satisfy the valency. And now acetate ion CH3CO, so it will get bonded from CH3 side. So 1 hydrogen will be less. So CH2COO minus. Similarly CH2COO minus. So like this. So this is the structure of ethylene diamine tetraacetate ion. Now in this case, if we look for the donor atoms, then first donor atom will be nitrogen, as it has one lone pair of electron over it. So another nitrogen, 2. Now this is negatively charged, this oxygen. So this is next, this oxygen, and this oxygen. It means how many donor atoms are there? 6 donor atoms are there. 2 nitrogen and 4 oxygen. And all these 6 donor atoms are involved in bonding at a time. So it means its denticity will be 6. And that's why this EDTA is called as hexadentate ligand. So all those ligands which have more than 2 denticity, they all will be included under polydentate ligand. Now one more thing, if you see clearly, when in this case the bond formation will be like this, if this is Mn plus ion, so simply if I make two ammonia molecules, one is like this and another is like this, so this is the bond. Here all these will make bond. Now if you see in this case and this case, the monodentate ligand and bidentate ligand, then in bidentate ligand a closed ring-like structure is formed. This one, closed ring. In this case also, if all these donor atoms are involved in bonding at a time, then several closed ring-like structures will form. If closed ring-like structure is formed, then that ligand is also called as chelating ligands. Chelating ligands. So chelating ligands are those which make closed structure by making coordinate bond with central metal ion. And this is not possible at all in case of monodentate ligand. This is always open because it is making only one bond. So this is possible only in case of bidentate and polydentate ligand. So bidentate and polydentate ligands are also called as chelating ligands. And all those complexes which have chelating ligands in them, they are called as chelate. I hope the concept of denticity is also clear to you. Now one more. Yes, so last one is ambidentate ligand. Ambidentate ligand. Ambidentate ligand are very important from examination point of view. Ambidentate ligands are those which have two ligating sites. Two ligating sites. Ligating sites means two donor atoms are available for donation of electrons, that is for making coordinate bond. But at a time, only one is involved. So all those ligands which have two ligating sites, but at a time only one is involved, they are said to be ambidentate ligand. The best example of ambidentate ligands are Cn minus, that is cyanide ion, then SCN minus, that is thiocyanate ion, and NO2 minus, that is nitrite ion. Now this Cn minus has two ligating sites. It can either make bond through carbon or it can make bond through nitrogen. But both the atoms are not involved in bonding simultaneously. Similarly, in thiocyanate ion, sulfur can be involved in bonding like this, or N can be involved in bonding. Isothiocyanate, when the bonding is through nitrogen, then that is called as isothiocyanate ion. And if sulfur is involved in bonding, then that is cyanate ion. Thio word is for sulfur. Whenever there is a word thio, it means we are talking about sulfur. Similarly, in NO2, it can also bond either through nitrogen or through oxygen. So all these three type of ligands have two ligating sites or two donor atoms available for bonding, but at a time only one is involved. Such type of ligands are called as ambidentate ligand. So this is all for today. Have a nice day. So today we have studied about coordination compounds, then the important terms that is central metal atom, counter ions, coordination entity, etc., related to coordination compounds. Thank you.